Welcome to homework.
So this time we're gonna go over a new problem, but it's still on diffraction. So we have a screen. Before the screen, we have a grating. So obviously, there's gonna be a gap where the light goes in, and so this gap, this distance, is d. And it so happens that we have 350 rulings. That's for the entire length per millimeters. And there's incident white light coming in. So all this is white light. This one right here, this is white light coming in. And on the opposite side, obviously there's gonna be a screen. And that screen takes in the light and produces a spectrum. We've always had the central maximum right here in the middle. So that's the central maxima. And the gap between the screen and the grating is d equals to 30 centimeters. Obviously, at some point, we're going to have to change that to meters. And on the screen, there's a hole that's cut on the screen, and we do know that the inner edge of the hole, you know, if you think about a hole being cut on the screen, the inner edge, the hole itself, the hole itself is 10 millimeters. And the inner edge of this hole, so this distance right here, is equivalent to 50 millimeters. So we have a hole that's cut right there, and then, you know, the distance from the central maxima up until the inner edge right there happens to be 50 millimeters. That's the information that's given. And then we want to find, in part A, the shortest. And then in part B, we want to find the longest. And by shortest and longest, we mean the wavelengths of the light, that passes through the hole. Okay, the light that passes through the hole, and obviously the inner edge is parallel to the central maxima. They're parallel. That signifies the distance between them being 50 millimeters. So we're just going to jump into the next page, and we have to do some conversions. We do have 350 rulings per millimeter. That's what we have. So D becomes each millimeter takes in 350 rulings. And so the inner edge is a distance y equals to 50 millimeters. If you go back, you see that this is that inner edge from the central maximum. That distance is 50. So we also do know that the gap between the screen and the gratings is 30 centimeters. And that produces an angle theta. So you have this distance d, and then you have the y. So this is d and y. So if you go back, you see that tangent of theta is opposite of adjacent. So theta has to be tan inverse of this ratio. We do have to plug in the value of y, which happens to be 50 millimeters, but we change it into meters. 1 meter is 1,000 millimeters. And then the distance d, we also have to change that to meters. 1 meter is 100 centimeters. And so it gives us an angle of theta being equivalent to 9.46 degrees. That's the value of theta. Obviously, prior to getting theta, we have to get that ratio, which is 1667. And then we move on and find the value of theta. So in the next page, remember, we were supposed to find two items. The first thing is the what do you call it? Well, the shortest wavelength, and then we want to find the longest wavelength. Recall the relationship between the maxima m lambda equals to d sine of theta. So m becomes d sine theta all over lambda. And obviously m is an integer, so any values we get have to be integers. D is 1 millimeter per 350. And so 1 millimeter per 350 times sine theta. Sine, we already had theta in the previous page, 9.46 degrees, and then we want to divide that by lambda. Our target is to get a lambda where m is an integer. So this becomes 4.7. If you simplify that, we have 460. That's going to be 460. We have to simplify that. So we get 460 nanometers of a lambda. We're using white light. So it just so happens that lambda has to be greater than 400 nanometers. That has to be our lambda. And since lambda is greater than 400 nanometers, we need to get m as an integer. And so lambda has to equal 460 nanometers. Lambda has to equal 460 nanometers. And that's the shortest wavelength. That's the shortest wavelength, or the shortest lambda. And then in the next page, we want to find the longest. Recall that we had a hole 10 millimeters, and then between the lower edge of the hole and the central maxima, we had 50 millimeters. And so we want to find the longest lambda. We have to first find theta, or maybe we could call it gamma. So we want to call that gamma instead of theta, or alpha. Okay, we want to call it alpha, just to distinguish it from the other one. Or maybe we want to call it theta prime, because they're always going to be theta. We want to call it theta prime. So this is theta prime to distinguish it from the other theta. So this whole distance is 60 millimeters. And then the gap between these two is d, which happen to be 30 centimeters. So we have tangent of theta prime equals to 60 millimeters all over 30 centimeters. Obviously, you want to change that to meters. So this is 60 millimeters times 1 meter over 1,000 millimeters. You want to divide that by 30 centimeters times 1 meter over 100 centimeters. And so theta prime becomes tan inverse of 0.2, which is approximately 11.31 degrees. In the next page, we already have that angle, and we know that m is 1. So m lambda prime equals to d sine theta prime. This was on the higher side, so we're using primes. This is 1, so lambda prime is d sine theta prime. And this becomes 1 millimeter over 350 sine of theta prime, which is 11.31 degrees. Then we simplify this problem, so we could change everything to nanometers. So we have 5.6 times 10 to the negative 4 millimeters. Change it to nanometers, so 10 to the 6 nanometers per millimeter. So we end up having 560 nanometers. And that happens to be the longest wavelength. So once again, we had two options in this problem. We had to find the shortest and longest wavelength. We're given white light coming through at perpendicular to the gratings, 350 rollings per millimeters. So the gap between the lower end of this hole, there's a hole right there, and the central maxima is 50. The hole itself is 10 millimeters. That's the information we're given. We went ahead and found the angle theta, given that y is 50 and d is 30. So theta was 9.64 or 46, sorry. And we're assuming m is an integer. And obviously lambda has to be greater than 400 nanometers because this is white light. So we end up having 460. We move ahead to find the longest wavelength. This time, of course, we're going to put together the gap in the hole and the gap in the, not the gap, but the distance between the lower edge of the hole and the central maxima. That's 60 millimeters. Using tangents, we found the angle between those two to be 11.31, the angle between these two. And then we went ahead and, assuming m is 1, we simplified the longest wavelength to be 560. Hope you enjoy the problem. Feel free to send any questions or comments, and have a wonderful day.